Okay, so the title of the talk is Simplicity and Scientific Progress. So if you look at Ilkka Niinilaudon's SCP article on scientific progress, he has this way of taxonomizing 20th century philosophy of science into two schools. So there's the synchronic school, which is focused on the finished products of science, and then there's the diachronic school, which is focused on scientific change. So when I first saw this taxonomy, I liked it a lot because I finally felt like there was a home for me in philosophy of science in the diachronic school, and but I would like to adapt this distinction a little bit. So for me, this is how I look at things. So the exemplar of a synchronic philosophy of science is confirmation theory, and my personal exemplar for a diachronic philosophy of science is learning theory. And these have kind of analogs in traditional epistemology, evidentialism and virtue epistemology. And so how do I understand these things? So in philosophy of science, a confirmation theory is about coming up with the correct relationship of confirmation that is like a logical relationship between a piece of evidence and a piece of theory. So it's all, time is kind of irrelevant, but you can sort of think of it as evidence and evidence at time t with relationship to some theory that you're evaluating. And in epistemology, evidentialism is about evaluating certain kinds of attitudes with respect to the evidence that you have at hand at any given time. So it's given that the evidence that you have right now, we want to evaluate your various belief attitudes. Are they rational? Are they supported by the evidence, etc.? Now, diachronic philosophy of science, and of course I have in mind learning theory, is slightly different. You want to justify various kinds of learning methods by proving things about their learning dispositions, by demonstrating that they have certain good-making learning dispositions. And in virtue epistemology, it's something similar. You want to evaluate not individual attitudes at a given time, but entire characters with respect to their virtues, which has something to do with their dispositions to behave over time. And so in this talk, I'm putting a little love in the upper right-hand corner. So Loudon, in his book, Progress and Its Problems, in the introduction, he gives like a kind of manifesto for the diachronic school. And I really like the rhetoric here, even though I don't agree with much else that's in the book. But this is what Loudon says. He says, progress necessarily involves a process through time. Rationality, on the other hand, and I think he has in mind Bayesian rationality, has tended to be viewed as an atemporal concept. Most writers see progress as nothing more than the temporal projection of a series of individual rational choices. And we may be able to learn something by inverting the presumed dependence of progress on rationality. So let's say maybe what it is to be rational is to adopt a progressive kind of disposition, rather than what it is to be progressive is to be rational at every stage, something like that. Now, in epistemology, in his 1992 book, Convig says something similar. He says, it's far from obvious that the best way of structuring a fruitful cognitive life is to concentrate on individual time slices and whether knowledge or justification is possessed at each time slice, and let the totality get generated by cementing together the time slices. So, and I guess Convig is often cited as a virtue epistemologist. Okay, so if you're in the diachronic school in philosophy of science, you very quickly run into the problem of progress. So basically, the problem of progress is why is scientific method conducive to scientific progress? What does the stuff that we do in science have to do with making progress on our problems? I mean, there's a traditional story, of course. I mean, one traditional story is Popper's story. So science progresses through a series of highly testable conjectures, followed by dogged attempts at refutation, And personally, I've always found this picture kind of romantic. It's like a philosophy of science for existentialist heroes who subject even their favorite theories to withering criticism, and eschew the comforts of confirmation. But well, I think that this is going to lead to anything more than a series of bold mistakes yielding to new and bolder mistakes, right? Why is this process going anywhere? And Lakatos says something similar. He objects in this one paper. Popper offers a methodology without an epistemology or a learning theory, and confesses explicitly that his methodology may lead us epistemologically astray, and implicitly that ad hoc stratagems might lead us to the truth, right? So we need some kind of reason to think that the critical method is progressive, and we don't have one. Of course, Popper hoped to show that the critical method leads to theories of increasing truth-likeness. But his truth-likeness definition was famously trivialized independently by Tichy and Miller in the same year. And basically, they showed that under Popper's definition of truth-likeness, no two false theories were ever comparable. For any two false theories, neither one is more truth-like than the other one, which is not a very interesting idea of truth-like. Of course, the failure of Popper's definition of truth-likeness leads to a research program here. And we get more and more sophisticated iterations of the definition of truth-likeness that aren't subject to this problem. But in his book, I think Ninilaudo makes a kind of striking admission. He says, the problem of estimating verisimilitude is neither more nor less difficult than the traditional problem of induction. So it's like we wanted to make progress on this problem, and we reduced it to like another problem that we don't know how to make progress on. I found this a very striking admission. So like even if you had the right definition, it's like a metaphysical definition of truth-likeness, you wouldn't know when your theories are getting more truth-like, or why a preference for apparently more truth-like theories has anything to do with getting to the truth. And so I think there's a way out, and I've been thinking about this as the virtue ethical maneuver. So here's Linda Zagzebski in her book. She says, since justifiedness is a property of a belief, it's very difficult to adjudicate disputes if the belief is treated as the bottom level object of evaluation. Instead, we focus on the deeper concept of an intellectual virtue and treat the justifiability of belief as derivative. So it's like instead of focusing on beliefs, you move to virtues, which have something to do with disposition and character. And in the case of truth-likeness, we're talking about theories, a sequence of theories, and we want to be able to tell when when a sequence of theories is becoming more truth-like. But the virtue ethical maneuver says, okay, don't look at the theories, look at the methods and their disposition to improve over time. So that's kind of the move that I'm making. So say that a method for answering a scientific question is progressive, if and only if the chance that it outputs the true answer to the question is strictly increasing with sample size. And notice that so long as there is a true answer, you grant me that for a second, that notion makes sense, even if it doesn't make sense to ask which of two false theories is closer to the truth. So we don't need a notion of of truth-likeness in order to make sense of this kind of notion of progress. But okay, suppose none of the answers on the table are true. Well, this still makes sense because you can now use the theory of truth-likeness. So say that a method for answering a scientific question is progressive if the chance that it outputs the most truth-like answer is strictly increasing with sample size. Or maybe the most useful answer is strictly increasing with sample size. So this notion of progress is kind of parametric. You can sort of plug in the right good-making feature of a theory that makes it the goal of inquiry. Okay, it's going to turn out that strictly progressive methods don't usually exist. But progressiveness is like a kind of regulative ideal. We want to approximate it. So say that something is alpha progressive if and only if that the chance that it outputs the true answer never drops by more than alpha. Now, this picture is just a kind of illustration. It's not like you shouldn't take it too seriously. But on the x-axis, we're thinking of like we're collecting more data. And on the y-axis, we're plotting the probability that we output the right answer among the answers we're choosing between. And if there are precipitous drops in that chance, meaning sometimes getting a larger sample is like a dramatically bad idea because your chance of getting the right answer will drop precipitously. That's less progressive than the picture on the left, where there are no precipitous drops anyway. Now, surprisingly, many standard statistical methods are not even approximately progressive. So this picture is from Chernick and Liu's paper, The Sawtooth Behavior of Power versus Sample Size. And what they're graphing here is at a particular parameter, the chance of correctly rejecting some false hypothesis. And they show that like there are these, although that chance of correctly rejecting converges to 1 as sample sizes increase, there are some very precipitous drops. There are certain really unlucky sample sizes where getting more data is a bad idea. It sets you back significantly. Now, what does this mean? Like we can think about it from the perspective of replication. So performing a replication study with a larger sample and a lower chance of replicating successfully, it's not just epistemically perverse, it might be unethical. Like imagine this is a vaccine trial and you expose more people to potential side effects for a worse kind of epistemic performance. That might just like if you propose that study to the funding agency or whatever, they should reject it. That replication study. If you did your power analysis and this is what it looked like. So here's a theorem from my dissertation. So if the answers to a question can be enumerated in agreement with simplicity, then the question is progressively solvable. I don't expect you to understand what that means yet because I owe you a definition of simplicity. But it's just a kind of foreshadowing. And moreover, every approximately progressive solution satisfies a kind of Occams Razor. Now that's also foreshadowing because I haven't defined what these things are. But what I'm advertising, it's a non-circular epistemic justification of Occams Razor in statistical science. Non-circular because I don't assume any kind of Bayesian prior distribution over the possibilities. I'm not saying it's more likely that the truth is simple or something like that. And violating Occam's Razor means designing into your method a tendency to fail to replicate true results. So we have a connection to the idea of replication. And moreover, a carefully calibrated Popperian methodology, not any old Popperian methodology, but a carefully calibrated one can ensure that the degree of backsliding is arbitrarily low. Epistemic backsliding in the sense of these precipitous dips. Okay, so I just want to point out the connection with the synchronic and diachronic distinction. So traditionally, epistemic justification has been synchronically conceived. So here's Alan Baker in the SCP article on simplicity. It means justifying an epistemic principle requires answering an epistemic question. Why are simpler theories more likely to be true? Now, when you have that kind of synchronic standard, that leads to despair. So here is Loudon in a 2004 paper. No one has shown that any of these rules is more likely to pick out true theories than false ones. It follows that none of these rules is epistemic in character. But diachronic justification looks a bit different. Going diachronic allows us to demonstrate that a systematic preference for simple theories is a necessary condition for a diachronic notion of progress. And I think that's also a good epistemic justification. It's not like the only epistemic justifications have to guarantee that you probably have it right already. Okay, so a little sketch of the way that this stuff works. So suppose we have a set of possibilities, W, and these are, in the statistical case, sets of models or contextually relevant epistemic possibilities. Each of these models is going to determine a probability of distribution over the data. And your methods are driven by data. So since your methods are driven by data, picking out a model also fixes the probability that your method outputs various answers to the question. Why? Well, the model fixes the probability distribution over the data. Your method is driven by the data. It's a data-driven method. And so fixing a world or a possibility fixes the objective chances at every sample size that your method outputs various answers. A question is just a partition of the set of possibilities into a countable set of answers. And as a little bit of notation, fancy Q is the question, and Q sub M is the answer true in model M. So it picks out this element of the partition. What does it mean to be a solution to a statistical problem? A method, and these are like sets of functions, one for every sample size, they just determine something to do at every sample size, is a solution to a question if for every model in the set of possibilities, the probability that it converges, the probability that it outputs the true answer, the probability in M that the method outputs the true answer in M converges to 1 as N gets big. So as sample sizes get big, the objective chance that you output the true answer converges to 1. And we say that a question is solvable if it has a solution. What's a progressive solution? A solution to a question is progressive if the chance that it outputs, if in every possibility, the chance that it outputs the right answer is strictly increasing with sample size. And what is alpha progressive? Well, it just means that it's almost strictly increasing, meaning if it ever goes down, it never goes down by much. And a problem is progressively solvable if you can get those curves to be, get the wiggles in the curve down to be arbitrarily small. So you can squeeze the alpha to be arbitrarily small, but not 0. That's what it means to be progressively solvable. Now, I need a notion of refutability. So this is, say that a hypothesis is alpha refutable if there exists a consistent hypothesis test of that of H with significance level alpha at every sample size. What does that mean? It's there exists a hypothesis test of H, which if H is false, the probability that the test rejects converges to 1. And if H is true, the probability that it falsely rejects is always small. And we say that a hypothesis H is simply refutable if there exists one of these, if it's alpha refutable for every alpha. So you can get the bound on false rejection down to be arbitrarily small. And here, I'm just writing the same thing with limits. So a hypothesis is alpha refutable if there is a sequence of tests such that the probability that the test rejects in every possibility where H is false converges to 1 as sample sizes get large. And the probability that the test rejects is small, is always small for every sample size in all the possibilities where H is true. And then we say it's simply refutable when we quantify out alpha. Now I owe you a notion of simplicity. And this notion of simplicity is inspired by Popper's. It's not, but here's Popper's notion of simplicity from the book. For any, oh, whoops, something went wrong. This is Popper's definition. For any two sets of models, say that A is for any two models. No, what's on the slide is correct. For any two sets of models, meaning for any two hypotheses, A is as simple as B if all the refutable consequences of B are refutable consequences of A. The problem with this definition is it confounds logical strength and simplicity because, well, if A entails B, then certainly anything refuting B refutes A. And we can just ignore the fact that we're talking about refutable consequences. If A entails B, then it's simpler. And this confounding logical strength and simplicity has some very perverse consequences because it means that suspending judgment is always a violation of Occams Razor. That seems like a very bad feature of this definition of simplicity. But we can say, fine, we fix the definition. We say for any two disjoint sets of models, say that any two competitors or competing answers to the question, say that A is as simple as B if all refutable consequences of B are refutable consequences of A, the standard like Popperian definition. That also has some annoying little problems, meaning the Tacon problem. So we think that like strictly linear, the set of all strictly linear equations is simpler than the set of strictly quadratic ones, and Popper's definition will give us that verdict, because if you ever refuted that if you're doing curve fitting, you're trying to fit a curve to some point, some scattered points. If you refuted quadratic, you would thereby refute linear, because quadratic can fit anything linear can, and anything that quadratic can't fit, linear can't fit either. But then it goes away if you start gerrymandering a bit and tacking on strange hypotheses. For example, either the curve is linear or the cat is on the mat is no longer simpler than quadratic. So the definition that we go for is just a slight modification. We say that for any two hypotheses, A and B, A is as simple as B if and only if all refutable consequences of B are consistent with A. And that returns the usual verdicts, like linear is going to be simpler than quadratic, or universal hypotheses like all ravens are black will be simpler than the catch-all, not all ravens are black. So here's one of the results, the big results from the dissertation. So if you can enumerate the answers in agreement with simplicity, meaning you never have to put something simpler, you have a bunch of hypotheses, you line them up, and you never have to put anything simpler after something more complex in the enumeration, then it's progressively solvable. You can get the degree of backsliding to be arbitrarily small. And you can do it with a carefully calibrated Popperian method that just tries to falsify the first one. When it falsifies, and conjectures the first one until it's falsified, and then once it's falsified, conjectures the second one until it's falsified, and so on. The kind of straightforward Popperian thing to do. So here's a now I owe you a definition of Occam's Razor. So we define simplicity. So what's Occam's Razor? A solution to a statistical problem satisfies Occam's alpha razor if in each possibility the chance of conjecturing an answer more complex than the true one is bounded by alpha. So Occam's Razor means always err on the side of simplicity, or anyway, with high probability. To write this in math, so a solution satisfies Occam's alpha razor if and only if whenever the true answer in M is simpler than some other answer, the probability in M that you conjecture that other answer is small. So the probability that you conjecture anything more complex than the truth is small. So, and then the big theorem is this. So every alpha progressive solution to the question satisfies Occam's alpha razor. So that shows that Occam's razor is a necessary condition for a certain kind of diachronic virtue, meaning a certain kind of progressive convergence to the truth. It's non-circular because we don't impose any kind of Bayesian priors. And it's epistemic because, well, progressiveness, I would say, is an epistemic virtue. And a carefully calibrated Popperian methodology, like the one I sort of sketched before, can ensure that the degree of backsliding is arbitrarily low. So anyway, that's the punchline, which we got to.